Welcome to learning modules. I am Dr. Gopalakrishnan, professor in the Department of Anesthesiology. Today we are going to see about the acid-base disorders and their diagnosis. Learning objectives, outlining of metabolism of nutrients, to explain the types of basic acid-base disorders, assess the degree of compensation, identify the mixed disorders, utilize the delta ratio and delta gap, manage the serum potassium level deviations. So contents, it will be split into these headings: introduction, simple disorders, then mixed disorders, anion gap, delta ratio and delta gap, serum potassium level deviations. First, we have to understand that life is acidogenic. The normal end products of metabolism. You see, carbohydrates on complete combustion produce carbon dioxide, on incomplete combustion produce lactic acid. Fat, on complete combustion it produces carbon dioxide, and incomplete combustion produce keto acids. Proteins, they produce bicarbonate and ammonium ions, where the carbon dioxide combines with the water to form the carbonic acid in the blood, which dissociates back into hydrogen, H2O and carbon dioxide in lungs. The carbon dioxide is washed out through the lungs. When you take the protein metabolites, bicarbonate and two molecules of ammonia unite to form the urea. This urea formation is by the liver and it is excreted by the kidney. Acids produced in the metabolism, they dissociate into H plus and anions. The excess hydrogen ions affect the enzymatic machinery. So we are very much concerned about the hydrogen ion concentration. Excess hydrogen ion concentration is called acidosis. Low hydrogen ion concentration is called alkalosis. How we measure this? We measure as pH. pH is negative logarithm of hydrogen ion concentration. So if you take the concentration 40, 50, 32, the 50 hydrogen ion concentration will have a lower value, while 32 will have a higher value. So when you see the pH range from 7 to 8, these are all the hydrogen ion concentration. At the pH level of 7, that is water, we have 100 nanomoles. At the pH of 8, we have 10 nanomoles. So the biological mechanisms operate between 7.36 to 7.44, that is around 40 nanomoles per liter. Normal values 7.4. So range is 7.35 to 7.45. So hydrogen ion concentration will be around 40, that is 35 to 45. If you take carbon dioxide, reference value is 40, range is 35 to 45. Bicarbonate is 24 milliequivalents per liter. The range is 22 to 26. See here, the carbon dioxide combines with water to form carbonic acid, which dissociates into hydrogen and bicarbonate. So this carbon dioxide can be handled by lungs, and bicarbonate can be handled by liver and kidney. In liver, it forms the urea, and kidney excretes the urea. So whenever there is a change in the pH, that is acid-base balance disturbance, we have buffers. The buffers act immediately and try to compensate for this change. Usually a buffer is a weak acid and its salt, or a weak base and a salt. So in extracellular, bicarbonate buffer and plasma protein buffers are stronger. Intracellular, proteins and phosphates are the strong buffers. In CSF, bicarbonate is strong. In urine, phosphate is the strong buffer. So this shows the relative change in the bicarbonate level to the pH level. See, at each level, that is at PCO2 40 mm, there is called isobar. So at PCO2 40 mm, the relation is this much. At 20 mm of mercury, this is the relation. So at 60, this is a relation, and at 80, this is the relation. So the relation between pH and bicarbonate changes according to the partial pressure of carbon dioxide. So there are four quadrants. Say, imagine that A is normal. On the right side is alkalosis, and the left side is acidosis. Here is the bicarbonate. Above is metabolic alkalosis. Below is metabolic acidosis. So we have importantly four components, quadrants. So let us try to understand. Acidosis. See, look at the pH, it is 7.3. It has decreased. So there is excess hydrogen ions. Now we have to look at the carbon dioxide level. See here, carbon dioxide is excess. Because of the excess carbon dioxide, there are more carbonic acid, and that has produced the more hydrogen ions. Here, the accumulated acid is carbonic acid. So it is also called volatile acid. When the acidosis occurs due to excess carbon dioxide, it is called respiratory acidosis. So what happens to the bicarbonate? When carbonic acid increases, both hydrogen ion and bicarbonate both will increase. So bicarbonate is also increased in respiratory acidosis. Now look here, pH is 7.28. So that is pH is low. That means there are excess hydrogen ions. Look at the carbon dioxide, it is normal. So that means carbon dioxide is not the source of hydrogen ions. There is some other acid. So the accumulated acid is not bicarbonic acid, carbonic acid, but it is some other acid. And it is called metabolic acidosis. So the excess hydrogen ion combines with the bicarbonate and reduces the bicarbonate level. So we have a low bicarbonate and a low pH. But the lungs try to compensate by removing part of carbon dioxide. So when the carbon dioxide goes down, carbonic acid goes down, hydrogen ions also will go down. So this tries to reduce or compensate for the metabolic acidosis. This is called respiratory compensation for a metabolic problem. So the accumulated acid is not carbonic acid, some other acid that is not volatile. Carbonic acid is called volatile acid because it can be excreted through the lungs. Now coming to this alkalosis. Look at the pH, it is on the higher side. So there is less hydrogen ions. Look at the carbon dioxide, there is less carbon dioxide. So the PaCO2 is reduced. So the reduction in carbon dioxide is the responsible reason for reduction in hydrogen ion concentration. So this is called respiratory alkalosis. That means the excess washout of carbon dioxide. But what happens to the bicarbonate? When carbonic acid is low, bicarbonate is also low. So both are low in a respiratory cause. Look here. So the body cannot remain the same. So when there is H plus ion deficiency, what the lungs do, they accumulate carbon dioxide so that there is increase in hydrogen ion to compensate. So carbon dioxide also increased. Bicarbonate is also increased. This is respiratory alkalosis. So now look at here 7.5 pH. So pH is high, that means concentration of hydrogen ion is low. Look at the carbon dioxide. So carbon dioxide has increased to compensate for the increase in bicarbonate. So this is respiratory compensation for a metabolic problem. Now, to have a look at all the conditions. For a respiratory acidosis, the kidney can compensate. For a metabolic acidosis, lungs compensate. In the case of respiratory acidosis, how the kidney can compensate? For acidosis, it reabsorbs more bicarbonate from the tubules, urinary tubules, or it can excrete hydrogen ions. So in both ways, the kidney can compensate. When it reabsorbs more of bicarbonate, the bicarbonate level will be high. So look at the 27 here, 33 here. By increasing the bicarbonate to 33, pH is brought to normal. Similarly, when you take respiratory alkalosis, there is low carbon dioxide and low bicarbonate. So how the lung can compensate? Say already there is less hydrogen ion. So you either excrete more bicarbonate or retain the hydrogen ion concentration to compensate. Look at here 22. But here the kidney has excreted bicarbonate so that pH is brought near normal. So this is the acute phase, this is the chronic phase. There is a difference between acute and chronic. This is partial compensation, this is maximal compensation. Maximal means it is bringing the pH to the near normal. One thing we should understand is compensations never overshoot. So don't diagnose abnormal conditions. How to understand the difference between acute and chronic? 1, 2, 3, 5. Instead of 1, 2, 3, 4, remember this as 1, 2, 3, 5. In acute respiratory acidosis, we expect for every 10 mm of mercury of carbon dioxide, bicarbonate change is expected is 1. So similarly 2, 3, 5. Now going to the examples. And respiratory system may compensate for the metabolic problem. How much to quantify? For a change of every milliequivalence of bicarbonate, in acidosis there is 1 mm of difference down, and alkalosis 0.75 up. And there is another way to find the respiratory compensation, that is called Winter's formula. For acidosis, it is 1.5 into bicarbonate plus 8. You reverse this number, 0.8 into bicarbonate plus 15 for metabolic alkalosis. So either you use 1.75 or Winter's formula to differentiate a respiratory compensation, whether it is abnormal or not. So never overdiagnose, compensations never overshoot. Now look at this. So 7.33, 70, 33. The pH looks almost normal, but the PaCO2 is 70. So look at the bicarbonate. So this is for every 10 change, we expect 1 in acute and 3 in chronic. Now from 40 to 70, there is increase of 30. So we expect 3 for acute, 9 for chronic. So 24 is the basic level. If you apply 9, 33, then this confirms chronic respiratory acidosis with maximal compensation. pH is brought to near normal. Now look at here, this is alkalotic end. PaCO2 is 30. It is respiratory alkalosis. But when you have to apply whether the 1, 2, 3, 5 rule, there is a difference of 10. Now if it is 2 per 10, it is acute, 5 per 10 is chronic. So PaCO2 is decreased by 10. So expected fall is 2 in acute and 5 in chronic. So from 24, it has come to 19. So this is chronic respiratory alkalosis. Now look at this. This is acidosis. PaCO2 is 100. Bicarbonate is 36. So it looks like a respiratory acidosis. Now we want to differentiate a acute or chronic. So 60 means for acute 1, that is 6. For chronic, it is 3 per 10, 18. So add the 6 and the 18. When you add 6, 30. When you add 18, it is 42. So if it is 30, it is acute. If it is 42, it is chronic. But now it is not fitting into both. It is 36. So this is acute and chronic respiratory acidosis. That is, there is an acute exacerbation of bronchospasm, expiratory flow obstruction. Now, if I look at here, acute on chronic respiratory acidosis, patient has come to the casualty. The intern put the patient on ventilator, but the patient developed convulsion after 2 hours. So we wanted to take a ABG. ABG showed 7.50, PaCO2 is 42, bicarbonate is 26. So what's wrong? See, basically, the patient's baseline was 70, acute exacerbation we pushed up to 100. But ventilator management, the intern, the resident wanted the normal CO2, so he brought to 42. From 70 to 42, it becomes respiratory alkalosis for the patient. So this caused the convulsion. So permissive hypercapnia means you allow approximately 70 mm of mercury for this patient. So our aim should be only 70 mm, not the 40 mm. Now moving on to the mixed disorders. Respiratory acidosis plus metabolic acidosis. Respiratory, all these four combinations are possible. Now look at this. 7.24 is the pH. So acidosis. 70. Carbon dioxide is raised. It looks like respiratory acidosis. In a respiratory acidosis, bicarbonate also should increase, but here it has decreased. So this picture gives you my mixed disorder, that is respiratory acidosis plus metabolic acidosis. Both acidosis are there. So respiratory acidosis with low bicarbonate gives the diagnosis of metabolic acidosis. Where you expect this? Type 2 respiratory failure plus lactic acidosis because of the anaerobic metabolism. Now look at this alkalosis. PaCO2 is 28, bicarbonate is 33. So it looks like respiratory alkalosis. But when you look at the bicarbonate is high. So we expect a low bicarbonate in respiratory alkalosis. So obviously this is a mixed disorder. This gives the picture of respiratory alkalosis and this gives the metabolic alkalosis. There are two alkaloses in this patient. Where will you get this? Hyperventilation plus vomiting. Hyperventilation causes respiratory alkalosis, while vomiting causes loss of acid and metabolic alkalosis. So now next example is 7.28. So acidosis. Now we have a low PaCO2, low bicarbonate. So it fits into metabolic acidosis. But we have to apply the compensations. Now there is a change in bicarbonate is 6. So expected fall in PaCO2 is 6 into 1, that is 6 mm of mercury. But here observed fall in PaCO2 is 12, 40 minus 28. So what should be our interpretation? So there is a metabolic acidosis, but associatedly, additionally, there is an respiratory alkalosis. Example is acetyl salicylate poisoning, where the salicylic acid causes metabolic acidosis, while the hyperventilation causes respiratory alkalosis. Now look at this, it's alkalotic end, but PaCO2 is raised, bicarbonate is also raised. So it looks like metabolic alkalosis, but we have to check. So 34 means there is a 10 difference in bicarbonate. So for every 10 rise, we expect 0.75 multiplication. So we expect the rise in PaCO2 to 7.5. But observed here is 20 mm of mercury. How to account for this? So there is a primary problem is metabolic acidosis. There is an additionally respiratory acidosis. Where we get this? Post cardiac arrest or respiratory failure, IV soda bicarbonate without adequate ventilation. So soda bicarbonate produces carbon dioxide, while already the patient is on metabolic alkalosis. Anion gap. Now coming to the anion gap. Normally there is the electrical neutrality. That is total cations is equal to total anions. So what we measure, sodium is the measured cation, commonly measured. All others are unmeasured. We are ignoring potassium now. This is only 4 milliequivalents. So we are ignoring. On the other side, in the anions, we measure chloride and bicarbonate and we don't measure other things. So look at here. This is the combination. So normally unmeasured anions are more than the unmeasured cations. This forms the anion gap. So unmeasured anion minus unmeasured cation is equal to this is sodium minus bicarbonate and chloride. So the normal anion gap, so look at here 145, 105, 24. So 145 minus, you add these together, then you get 12. So the normal anion gap is 12. You can take the range is 8 to 16. Now look at here, there is a difference. Bicarbonate has fallen, but proportionately chloride has increased. See here, bicarbonate is less, but chloride has increased, so the difference is still 12. It is maintained. So this is called metabolic acidosis with normal anion gap. But look at here, 145, chloride is 101, bicarbonate is 14. Chloride has not increased, but bicarbonate is low. So the total falls low. So the difference becomes 30. So this is called metabolic acidosis with wide anion gap. So now you see the metabolic acidosis. You are confirming with the PaCO2 and bicarbonate. So this is metabolic acidosis. So in the following slides, you will have metabolic acidosis. You have to concentrate on the sodium and the chloride. Now what is the anion gap? 130 minus 102 plus 14. The anion gap is 14. This is called normal anion gap metabolic acidosis. See here the same picture, metabolic acidosis, but sodium is 130, chloride is 94. So when you add 94 and 14 together and subtract from 130, you get 22. This is called wide anion gap or high anion gap. So in normal anion gap, accumulated acid is hydrochloric acid. In high anion gap, some other acid which we are not measuring. So some other acids. Both give excess H plus ions. So where you will get normal anion gap metabolic acidosis? Either it could be a bicarbonate loss or a ineffective hydrogen ion secretion. So bicarbonate loss commonly in diarrhea, proximal tubular acidosis, erythrosigmoid ostomies. But in distal renal tubular acidosis and Addison's disease, there is ineffective hydrogen ion secretion. So in high anion gap, there is also excess H plus ion, but the acid is different from hydrochloric acid. There is some other acid like lactic acidosis in hypoperfusion or liver failure, ketoacidosis in diabetic patients or alcoholic or starvation, renal failure patients, that is phosphoric acid and sulfuric acid, acetyl salicylic acid, ethanol and glycol poisoning. So look at here, metabolic alkalosis, bicarbonate accumulation. So metabolic alkalosis occurs when bicarbonate accumulates or hydrogen ion is lost, that is acid is lost. For example, vomiting of gastric juice. Gastric juice is rich in acid. So when it is lost, it causes alkalosis, metabolic alkalosis. If somebody go for ingestion or intravenous bicarbonate, you are disturbing the balance, so the bicarbonate level goes up, it causes metabolic alkalosis. Then it is called contracted blood volume. In contracted blood volume, sodium is retained at the expense of hydrogen ions. So in metabolic alkalosis, we have two types, saline responsive and saline non-responsive. Saline responsive, normal saline, when restoring the volume, contracted blood volume, the pathology corrects by itself. Saline non-responsive means endocrine disorders. Now coming to the important point, delta ratio and delta gap. So we have understood what is normal anion gap, 12, 8 to 16. How you are going to calculate sodium minus chloride plus bicarbonate. Now we are going to compare the change in the anion gap versus change in the bicarbonate. That is delta anion gap, delta gap by the delta bicarbonate. Now look at this example. First example, 130, 102, 14. The anion gap is 14. What is delta anion gap? How much is the anion gap changed? It is only 2. See here, it is 130. Anion gap is 21. The delta anion gap is 9. See here, chloride has also gone down. So the anion gap is 22 and the delta anion gap is 10. Now look at the change in the bicarbonate. Here 10 is lost, 10 is lost, but here only 4 is lost. Now how we are going to interpret this? So delta ratio means delta gap by delta bicarbonate. Here it is 0.2, here it is 0.9, here it is 2.5. So interpretation up to 0.4 is pure normal anion gap. 0.4 to 0.8 is mixed. 0.8 to 1.2 is still high anion gap. More than 2 high anion plus metabolic alkalosis. How to understand this? Now look at the another scenario, 7.4. pH is near normal, bicarbonate is 40, the bicarbonate is 23, PaCO2 is 40. It looks perfectly normal, but until you see the sodium and chloride, here 132, 90. So what happens to the anion gap? It increases. It is called high anion gap metabolic acidosis. At the same time, it may have metabolic alkalosis. Now we are moving to the final part, triple disorders. So look at this, 7.2 acidosis, 65 confirms the respiratory acidosis, 22 it looks like there is a metabolic acidosis component. So bicarbonate we expect it to be higher, but here it is lower. So there can be a metabolic acidosis component. Also we have electrolytes 136, 98. Okay. Now we say respiratory acidosis with the low bicarbonate. So this gives you the diagnosis of metabolic acidosis. Now going to the triple disorder proper. Now anion gap is 19, delta anion gap is 7, that is from 12 it has gone to 19, so it is 7. Bicarbonate change is only 1 or 2. Now we are going to compare the delta gap and delta bicarbonate. That is 7 by 1, the ratio is 7. So what happens to the potassium ions and sodium ions? In most of the cellular membranes, sodium is retained at the cost of potassium and hydrogen ions. Look at here, sodium is exchanged and correspondingly potassium and hydrogen ions are reaching here, both in the blood as well as in the urinary tubules. But look at this situation. In metabolic acidosis, there is excess H plus. So this excess H plus is exchanged with the sodium. So the urine contains acidic urine. Look at here. So what happens in alkalosis? In alkalosis, there is less hydrogen ions. So less hydrogen ions are available for sodium exchange. So what happens? Potassium leaves this area and goes to opposite side. So we get a hypokalemia, which is a relative phenomena. Now, you see, potassium is low. So no other go, hydrogen will be exchanged. So when the potassium is low, it causes hypokalemia. On the contrary, hypokalemia can cause metabolic alkalosis. So both are occurring at the same level. Either of one, they can lead to the other. This is a special situation where there is paradoxical aciduria. There is acidosis. If there is acidosis, then we expect a acidic urine. But in alkalosis, we don't expect a acidic urine. It happens in certain situations where hydrogen ion is there, potassium is not there, sufficient potassium is not there. And hydrogen ion is also less. So this is a situation like pyloric stenosis, where the gastric juice, which is rich in hydrogen acid, hydrogen ion is lost by vomiting. So when hydrogen ions are lost, it produces metabolic alkalosis. This causes potassium level, low level also. So when hydrogen ion is less, so the potassium ions are exchanged for sodium, so resulting in hypokalemia and paradoxical aciduria. So when you see a hyperkalemia, what shall we do? Whether we want to supplement or no need, or in fact restrict. So in DKA, hyperkalemia is a relative phenomena. When you give insulin, it will push the potassium inside the cells, so you need to supplement. In lactic acidosis, it is just a perfusion problem. So when you correct the perfusion, the level becomes normal. But in renal failure, you should not given potassium. You should not given even oral, that is tomatoes, bananas, coconut water. So in the summary, ABG is easy to understand, not a puzzle. The accurate diagnosis and high degree of suspicion about mixed orders will increase the clinical acumen. Most important factor is compensations never overshoot. So never overdiagnose any disorders. We need just 3 seconds to identify the single disorder, 8 seconds for the two disorders, and 15 seconds for the triple disorders. So we need not take more time. We should have a clear concept and understand well. The potassium level managements differ as per the etiology. That is, whether to give supplement or do not act anything, no need, or you have to restrict the potassium. This depends on the etiological factors. Thank you very much. I hope you would have enjoyed the acid-base disturbance. Though it is a difficult topic, we have taken efforts to simplify it and explain it.